Okay, class, we're going to pick back up on lecture chapter two. This is part two of two, so we're going to conclude chapter two with this lecture. And I'm going to go ahead and start sharing my screen here. Okay, so as you can see, we are now into acids and bases. We've already talked a little bit about the properties of acids and bases with protons and hydroxyl ions, but basically, hydrogen ions spontaneously generate in pure water by just dissociation, or what we would call ionization of a small, it's just a small percentage of water molecules that go into equal numbers of hydrogen ions and hydroxide ions. So if you put these two together, you can see that that would be H2O or water, but it will break down spontaneously into this dissociation of hydrogen ions and hydroxyl ions. Acids and bases change the balance of hydrogen and hydroxyl ions. So basically, you'll get an accumulation of either hydrogen ions or hydroxyl ions, whether you're in acids or bases. So an acid is a substance that's going to increase hydrogen ions in solution. A base is just the opposite. It'll increase uh, concentration of hydroxyl ions because you're decreasing your hydrogen ion concentration in solution. So you always kind of think of it as how much hydrogen ions do we have in solution, and that is what makes it either an acid or a base. pH is just a scale by which scientists use to describe whether a solution is acidic or basic. So the pH scale again ranges from 0 to 14. Anything below 7 is going to be acidic, anything above 7 is alkaline. And the extremes in pH in either direction from that middle neutral point of 7.0 are usually inhospitable to life, but there are exceptions like what we see down on like deep sea thermal ocean vents that are, pretty acidic conditions. We see life teeming there actually. So there are what we call acidophiles that like acidic conditions, that kind of thing. But here's just the pH scale again represented on scale. This one's flipped from how we've seen it in the past, where 0 is at the top. So this is the most acidic down to the most basic. So again, you can see here the acid solution has a lot more hydrogen ions than hydroxyl ions. Here in this neutral solution, you have an equal number. And then in the basic solution, you have a lot more hydroxyl ions than you do hydrogen ions. So buffers, they're going to be essential for the pH homeostasis of living things. They absorb excess hydrogen and hydroxyl ions, maintaining that stable pH. And most buffers are compounds that convert between acting as a weak acid and a weak base. So this is the bicarbonate buffering that happens in your blood to make sure that our body maintains a homeostasis. So the body buffers the pH by using this. Now, the blue arrows show the process of raising pH as more CO2 is made. The purple arrow indicates the reverse, so it's lower in the pH as more bicarbonate is created. So um, as more CO2 is created, we actually get a increase in the pH. So what that does is that basically you're becoming more alkalinic, and then if you need to lower the pH, more bicarbonate is made. So that's just the system right there with the arrows. So let's talk about carbon a little bit. Carbon is the backbone of life, and living organisms are going to consist mostly of carbon-based compounds. Carbon is unparalleled in its ability to form large, complex, and varied molecules. Proteins, DNA, carbohydrates, and other molecules that distinguish living matter are all composed of carbon. Organic chemistry is the study of compounds that contain carbon regardless of origin. And so organic compounds are going to range from simple to very, very large compounds. So now, one thing you need to know is that organic compounds are always going to contain carbon, but not everything that contains carbon is considered an organic compound. So, like carbon dioxide, carbon monoxide, those are inorganic compounds, even though they contain carbon. So, if it has carbon in it, It's most likely going to be an organic compound, but not always. But if it does not have carbon in it, it's always inorganic. Carbon is versatile, so the number of unpaired electrons in the valence shell of an atom is generally equal to its valence number. So the number of covalent bonds it can form is based on the number of unpaired electrons. So if you look here, hydrogen has 1 electron in its valence shell. Its valence number is 1. Oxygen has 2 in its valence shell, and it has actually 6, sorry, but its valence number is 2. So carbon has a valence of 4. So you see this is one of the exceptions where it's not always the same. Nitrogen is the same way. But basically you can look at carbon and it has 4, its valence number is 4. And it can create 4 single bonds or 2 double bonds. It can create 1 double bond and 2 single bonds, or 1 triple and 1 single, always adding up to be 4. So this 1 double bond takes up 2 electrons, 2 single bonds are a single electron a piece, that's 4. 2 double bonds are 4 electrons, 4 single bonds, 4 electrons, that kind of thing. So the shape of carbon molecule carbon molecules are going to be dependent on how many bonds it's making. So when it's in a 4 bonded configuration with we call this methane, it's in a tetrahedral shape. Basically, these hydrogen ions are or hydrogen molecules that are bound to carbon, are trying to get as far away from each other as possible. So they get in this equidistant arrangement called a tetrahedral in single bonds. If you put 2 carbons together, those 3 hydrogens connected to either one will try and get as far away from each other and from the others on the other side. So they form this tetrahedral shape where it comes in on itself like this. So you can see the triangle point here coming down, and this triangle point here coming down. So they're trying to basically get as far away from each other as possible. If you have a double bond so that makes you only have 2 hydrogens on each carbon, they're going to again try and get as far away, and it'll be a planar shape. So this is all in the same plane, where these are obviously not in the same plane. You can see this one is coming out of the screen here, where this one's going back into the screen. So when they form single bonds with other atoms, the shape is tetrahedral. 2 carbon atoms form double bonds. The shape is planar or flat. Hydrocarbons. Okay, so hydrocarbons are organic molecules consisting entirely of carbon and hydrogen. And many biological molecules are hydrocarbons and or have hydrocarbon base. So hydrocarbons can make a huge variety of structures due to carbon's versatility. In fact, like a lot of fuel that we use is hydrocarbons, like ethane, propane, butane. All of those are fuels that we burn, and they're very flammable, but they are considered hydrocarbons because they're made exclusively of carbon and hydrogens. So naming conventions, you're going to get more into this when you get into chemistry, about how double bonds make it an ene and triple bonds make it an ine and that kind of thing. And then if you get into cyclical, it'll be hexane, cyclohexane. And then this is very common, a benzene, where you have alternating double bond characteristics. So in a hexane, or a hexagonal shape, I should say. Isomers. Okay, so this iso prefix is very common in language that you're going to read throughout biology and chemistry. Iso just basically means same. So isomers are compounds with the same molecular formula but different structures and properties. Okay, so isomers are common in biological chemistry. The structure of isomers have different covalent arrangements, and the covalent, remember, is a sharing of electrons to form a bond. Geometric isomers have the same covalent bonds but differ in their spatial arrangement in cis-trans. And so this cis-trans is basically, if you were to, let's see if I can draw this out here for you. I'm going to just draw a line. All right, so if you have a chain here, and you have double bonds that are, we'll just say here in the structure, and you had a substituent that came out here that's a hydrogen, and you have a substituent that comes out uh, here that's a hydrogen, that's going to be trans because it's on opposite sides of the double bond. But if you had a substituent that looked something, or a chain that looked something like this, there's the double bond there, and you got a hydrogen sticking up over here, and you got a hydrogen sticking up over here, that is cis, okay, because they're on the same side of the double bond. So trans, opposite sides of the double bond. And I should erase this like this, and then yeah. But anyway, so you get the picture. It's on the opposite side of the double bond. I'm just highlighting in here. There would be another bond here, but I wanted to make sure you understood that there's double bond. It's on the opposite side, where cis is on the same. Okay, so we'll erase all that. Go back this. All right. So, what are enantiomers? So they're isomers that are mirror images of each other, non-superimposable mirror images. So you can think of like your hand for enantiomers. Basically, if you were to look at your hand and you hold them facing each other, the thumbs are going to be pointed back at you. Like if you put your palms together, your thumbs are both pointing back at you. Your pinkies are pointing away from you, and that is a non-superimposable mirror image, because if you were to now flip and face your palms towards yourself like that picture is, one thumb is facing out towards the left, your right thumb is facing out towards the right. So if you were to try and overlay those palm to back of your hand, and so that they're facing the same way, they can't impose over themselves. So that's what an enantiomer is. It's a mirror image, non-superimposable mirror image. All right. So the chemical groups most important in the process of life. Many biological chemicals are important, and they're most often going to have hydrocarbon bases modified with functional groups. So what are functional groups? Functional groups are the components of organic molecules that are most commonly involved in the chemical reaction. So that's a key to remember. The functional group is the one that's the group that's most commonly involved in chemical reactions. The number and arrangements of these functional groups give each molecule its unique properties, like its melting point and boiling point, and whether it gives off an odor, and that kind of thing. So the functional groups are going to be responsible for its unique properties. The chemical groups most important in the process of life continued, and we basically said they're going to be modified with these. I think I accidentally put two slides in back to back. Sorry about that. And so let's just talk about a couple of these. 7 functional groups that are most important in chemistry life are hydroxyl groups. So we talked about what that was already. That's the OH minus group. A carbonyl group is just basically a a carbon group bound to something. A carboxyl group is going to be a double bonded carbon to oxygen, is a carboxyl group. An amino group is going to be an NH, nitrogen bounded to 3 hydrogens. A sulfhydryl group is sulfur bounded to hydrogen. Phosphate is obviously a phosphate group it just has the P bounded oxygen. Methyl is going to be a carbon bounded to 4 hydrogens. So these are very, very important. And then here is their structures. So let's look at this. The OH, carbon double bonded to oxygen, is the carbonyl group. Carboxyl group has the carbon double bonded to oxygen with an OH group. So carboxylic acid, that's what is indicative of that. Here's acetic acid drawn. So this has, this shape, but what's in purple is the important part. That's the carboxyl group. So carbonyl is just basically a carbon double bonded to oxygen. This could be a ketone where it's just in a chain of other carbons, or like this acetone, where it's just basically, this is a ketone group, or it could be a like propanol, is basically just a hydrogen bonded to it. So you know, basically just the part in purple is the carbonyl group. So down here, amino group is the nitrogen bound by two hydrogens. And depending on whether this substituent is a um, uh, primary or secondary or tertiary bound. Right here, you can see it's bound to three hydrogens in this case. So, you know, it can be bound to more than two hydrogens. But basically, nitrogen bound to hydrogens amino group. Sulfhydryl, a sulfur and a hydrogen. Phosphate, a phosphate group bounded to oxygens, and a methyl group is you know, is a carbon bound to hydrogen. So in this case, it's only bound to two hydrogens over here in methyl cytosine. So, but here in conventional form, it's bound to three hydrogens. So just remember, carbon bound exclusively to hydrogens like that is a methyl group. All right, so alcohols. Alcohol is this OH group. When this OH group leaves, it becomes a hydroxyl group. So alcohols are always going to be an oxygen bound to a hydrogen. That's an alcohol group. We call them hydroxyls. So carbonyls, just a little bit more exclusively, we broken down. This is all just broken down from that chart that we just saw. So I'm not going to go over these again, but you need to understand and be able to identify that this is a sulfhydryl group. Um, and then this is a phosphate group, but this is very easy. If you see a P, phosphate. If you see a S, sulfhydryl. If you see an N, amino or amine. Carboxyl has the OH. Carbonyl is just the C bound to O in between other C's. That's a carbonyl group. Or carbonyl is another way of pronouncing it. So carbonyl. All right. So, and then methyl carbon with hydrogens. It's like, you know, it's going to be stuck out there on its own. Um, all right. So here's the study guide, what we went over for all of these lectures. You need to be able to answer these questions. And this is it continued on. So just make sure that you are very familiar with these questions and can answer them. If you're having issues with some of this, I know chemistry can be a little difficult and confusing. I'd be happy to jump on a Zoom with you. So just email me and we can do a private tutoring session. But other than that, this concludes chapter 2 study